Hi, my name is Alex, and in this video I'm going to show you how to set up a basic PID controller using TIA Portal, and also a water tank simulation, where his level will be controlled by a PID. So let's go because we don't have time to lose. Okay, so the first thing we need to do is to create a cyclic interruption block, the OB30. This block interrupts the main program, OB1, every given time. Our PID will be inside this block instead of the OB1, as we usually do with other kinds of programs. So we're going to go here, add new block, select cyclic interrupt. Here at cyclic time, we can leave the default value for our application. Okay, once it's finished, now we need to insert the PID controller. For this, we're going to go here at Technology menu, PID Control, Compact PID, and here's a quick tip. The PLC SIM v13 does not work with the PID Compact version 2.2, so you should use the version 1.2 for simulation purposes. You can select the version here. So let's drag the controller inside of this block, create the new DB, set a block. Okay, so this is the PID compact block. You can see here there are three kinds of inputs and also three kinds of outputs. Set point for the reference value, input for process value, PV, a real value, and input PER, also a process value, but usually an analog value from an I/O, ranging from 0 to 27,648. The three outputs are output for real values, output PER for analog values, also ranging from 0 to 27,648, and output PWM for pulse width modulation, usually used on heater resistors to temperature control. You must click here for the configuration window to start the setup. Here at the basic settings, you have the controller type, which you can tell to the controller what kind of process he will control. In our case, I will select volume, and the unit will be liters. Here, at inputs and outputs parameters, we're gonna set where is the default input and where is the default output. In my case here, I will use the input, normal input for input, and the output PER to the default output. Okay. At process value settings, we must set the process value limits. In my case, I will set 300 liters for the high value and 0 to low. These values correspond to this scale in my simulation. If you use input PER, you'll need to set up the process value scaling as well. In my case, it won't be necessary. At advanced settings, you have process value monitoring, where you can set an alarm for the output if you want to, only if you want to. PWM limits, you can set the minimum on and off time, like the minimum daily cycle, but only if you use the PWM output. Output value limits, if you want to cap your maximum or minimum output. And finally, the PID parameters. PID stands for proportional, integral, and derivatives. and is the most popular control algorithm used today. Those three parameters must be well adjusted for better performance. The proportional action, also known as gain, produces an output proportional to the error. The higher the error, the higher the output. If the proportional action is too weak, the system can't overcome the disturbances. If it's too strong, the system tends to get unstable. The downside of this kind of controller is an offset error. The integral action time. It speeds up the system's response to error and eliminates the offset. If the action is too weak, the system will take too long to reach the set point. If it's too strong, the system also tends to get unstable. Derivative action. It makes the system react anticipating the error, creates a stronger output according to the error's speed. It should not be used on systems which deals with constant disturbances, because it tends to create more instability. So here we have the three main PID parameters: gain, integral action time, derivative action time. The derivative delay coefficient delays the time of the derivative action. The greater the value, the longer it takes for the derivative action to kick in. The proportional and derivative action weighting weakens the effect of those actions to the set point, so it attenuates the output action. Sampling time, you can leave the default value. Turing rule. Here you can select whether you want to use PI or the PID structure, since derivative action should not be used in some cases. Well, that's pretty much it. Now let's get practical. Okay, here we have our empty tank, our HMI set to manual, and now let's make some tests. First, I will show you the effects of the proportional action alone. So let's set point for 100 and the proportional action to 50. Now let's start the PID controller. As I said earlier, this kind of controller has a stronger output at the beginning when the error is high, but a downside of this kind of action alone is it has an offset, an undershoot, which prevents the PV, the process value, to reach the set point. Now let's restart the simulation. And I'm going to show you what happens when we add an integral action to the mix. Let's set the integral action to 5 and start the PID controller again. As you can see, now the undershoot is gone. Actually, we have a little bit of overshoot. This is the PI structure that I told you before. Now, let's restart the simulation again. But this time, we're going to add the derivative action. Let's say around 50. And see what happens. Okay, I think we have seen enough. You see, now the controller senses that the PV is coming too fast and tries to slow it down by shutting down the output. These sudden changes in the output created oscillations in the water, thus making the water measurements oscillate as well. So we have to be really careful when adjusting the derivative action. Let's try again, but this time let's adjust all three parameters so we can safely add the derivative action. So let's try 5 to proportional, 20 to integral, and derivative just 1. Let's enable and see what happens. You see, the system reached its steady state with almost no overshoot. Well, now let's see what the PID self-tuning algorithm is capable of doing. Let's try it. Okay, now here's a great feature from TIA portal, the commissioning window. Here, there is a feature that can really help us, the pre-tune / fine-tune. With it, the controller can adjust itself those three PID parameters. To do this, first you must start sampling, so the system can monitor the set point and the process value for the tuning process. Here you have the tuning mode, where you can perform the tuning of your system. There are two kinds of tuning. Pre-tuning, when your process value is far from the set point, and fine-tuning, when your process value is too close to the set point. Basically, you can start a pre-tuning and the system will switch to fine-tuning by itself when the PV reaches a certain value. Here, you have the progress bar, where you can monitor the tuning progress. After the tuning is finished, you can upload the parameters to your PLC using this button over here. Now let's start and wait for the results. But first, I must go here to my HMI and switch the control to auto. And now let's start the pre-tuning. Your system is tuned. Well, this is pretty much it. I hope you liked the video and stay tuned for the next ones to come. Bye!